Dear students, we already know that every reflected ray of light follows the laws of reflection. That is, the incident ray, the normal at the point of incidence, and the reflected ray all lie on the same plane. The angle of incidence is equal to the angle of reflection. We also know that if a surface is highly polished, it reflects most of the light falling on it, forming an image as in the case of a plane mirror. The laws of reflection are applicable to all types of reflecting surfaces, including the spherical ones. You are already familiar with the formation of image by a plane mirror. Do you remember the properties of the image formed by the plane mirror? The image formed by a plane mirror is always virtual and erect. The size of the image is equal to that of the object. The image formed is as far behind the mirror as the object is in front of it. Further, the image is laterally inverted. Will the properties of the image formed be the same if the reflecting surfaces are curved? Let us explore. After this session, you will be able to differentiate between convex and concave surfaces, erect and inverted images, as well as real and inverted images. You will also be able to draw labeled ray diagrams showing the convergence or divergence of spherical mirrors, and also make ray diagrams pertaining to the image formation by spherical mirrors. You will be able to measure the physical quantities such as focal length of a concave mirror using an appropriate apparatus. Students, have you ever seen your image in any surface other than a plane mirror? Yes, you are right. You can see your image in all shiny objects, be it steel spoons or thalis or shiny polished floor, metal doors, body of a car, etc. These images do not seem to be the same as the image formed in a plane mirror. Why? Because these surfaces are not plane. Let us take the example of a shiny spoon. If you look at a shiny steel spoon, you can see your image on both of its surfaces. Is there a difference in both the images? Yes, because the reflected rays travel differently for each of the surfaces. Let us discuss this in detail. If the reflecting surface is caved in like the inside of a spoon, then it is called a concave surface. And if it is bulging out, it is called a convex surface. Is there any difference between the images formed on the inner side and the outer side of a steel spoon? To understand how they form images, we need to learn a few terms related to these. Spherical mirrors are known to be so because they can be imagined to be formed by cutting a section of a sphere silvered on one side. Before we learn further about the spherical mirrors, we need to recognize and understand the meaning of a few terms. These terms are commonly used in discussions about the spherical mirrors. The center of the reflecting surface of a spherical mirror is a point called the pole. It lies on the surface of the mirror. The pole is usually represented by letter P. Can you imagine the caved in or curved in mirror as a part of a spherical mirror? The reflecting surface of a spherical mirror forms a part of a sphere. This sphere has a center. This point is called the center of curvature of the spherical mirror. It is represented by the letter C. Please note that the center of curvature is not a part of the mirror. It lies outside its reflecting surface. The center of curvature of a concave mirror lies in front of it. However, the center of curvature of a convex mirror lies behind the mirror. You may note this in the figure which is there. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature of the spherical mirror. It is represented by the letter R. You may note that the distance between the pole and the center of curvature, represented in the diagram as PC, is equal to the radius of curvature. Imagine a straight line passing through the pole and the center of curvature of a spherical mirror. This line is called the principal axis. Remember that the principal axis is normal to the mirror at its pole. Let us discuss an activity to understand how the rays falling on these mirrors behave after reflection. Dear students, you must exercise caution while doing this activity and do it only under adult supervision. Take a concave mirror or a shiny concave surface. Try to focus the rays of sunlight onto a black paper. Hold the mirror such that a sharp image of the sun is formed. After a few minutes, you will observe that the paper starts to burn. But why? The mirror is focusing all the rays of sunlight falling onto it at a point. This point is called its focus, and the distance between the focus and the pole of the mirror is called the focal length. Try focusing the image of a distant object like a building or a tree onto a wall. The distance between the mirror and the sharp image of the distant object is approximately its focal length. Let us try to understand this observation with the help of a ray diagram. Observe the figure closely. A number of rays parallel to the principal axis are falling on a concave mirror. Observe the reflected rays. They are all meeting or intersecting at a point on the principal axis of the mirror. This point is called the principal focus of the concave mirror. Similarly, observe the second figure. How are the rays parallel to the principal axis reflected by a convex mirror? The reflected rays appear to come from a point on the principal axis. This point is called the principal focus of the convex mirror. The principal focus is represented by the letter capital F. The distance between the pole and the principal focus of a spherical mirror is called the focal length. It is represented by the letter small f. You have noticed that the rays after reflecting from a concave mirror actually converge or meet at a point in front of it. Hence, a concave mirror is called a converging mirror, and it forms real images whenever these images are formed due to the actual intersection of light rays. On the other hand, the rays after reflecting diverge in case of a convex mirror. They do not meet, they appear to diverge from a point. This mirror is called a diverging mirror. And as the rays never meet after reflection, the images formed by such mirrors are always virtual in nature because they are not formed by the actual intersection of light rays. The reflecting surface of a spherical mirror is by and large spherical. The surface then has a circular outline. The diameter of the reflecting surface of a spherical mirror is called its aperture. In the figure, distance mn represents the aperture. We shall consider in our discussion only such spherical mirrors whose aperture is much smaller than its radius of curvature. Is there a relationship between the radius of curvature capital R and focal length small f of a spherical mirror? For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice the focal length. We put this in the form of a relation as R equal to 2f. This implies that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. You have studied about the image formation by plane mirrors. You also know the nature, position and relative size of the images formed by them. How about the images formed by spherical mirrors? How can we locate the image formed by a concave mirror for different positions of the object? Are the images real or virtual? Are they enlarged, diminished or have the same size? We shall explore this with an activity. But before that, it is important for us to learn about certain special rays which are often used to frame images. For drawing ray diagrams, we generally consider an extended object of finite size placed in front of a spherical mirror. To construct the ray diagrams, in order to locate the image of an object, an arbitrarily large number of rays emanating from a point could be considered. We will consider only two rays for the sake of clarity of the ray diagrams. These rays are so chosen that it is easy to know their directions after reflection from the mirror. The intersection of at least two reflected rays give the position of image of the point object. Any two of the following rays can be considered for locating the image. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror, or appear to diverge from the principal focus in case of a convex mirror. A ray passing through the principal focus of a concave mirror or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. A ray passing through the center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. The light rays come back along the same path because the incident rays fall on the mirror along the normal to the reflecting surface. A ray incident obliquely to the principal axis towards a point P, which is the pole of the mirror, on the concave mirror or a convex mirror is reflected obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence, which happens to be the pole, making equal angles with the principal axis. As you can see in the figure, a ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror, or appear to diverge from the principal focus in case of a convex mirror. When we consider a ray passing through the principal focus of a concave mirror as shown in the figure, or a ray which is directed towards the principal focus of a convex mirror, after reflection will emerge parallel to the principal axis. If we consider a ray passing through the center of curvature of a concave mirror or directed in the direction of the center of curvature in case of a convex mirror, after reflection is reflected back along the same path. The light rays come back along the same path because the incident rays fall on the mirror along the normal to the reflecting surface. As you can see in the figure, a ray incident obliquely to the principal axis towards a point P, which happens to be the pole of the mirror, on the concave mirror or a convex mirror, is reflected obliquely. The incident and reflected rays follows the laws of reflection at the point of incidence, that is the pole, making equal angles with the principal axis. We will now try to frame images using concave mirrors. Let us consider the object to be placed at infinity. The light rays incident from infinity can be shown with the help of a parallel beam of rays. As you could see in the diagram, the rays will converge at the focus, forming a real, inverted and highly diminished image on the screen. Now we will move on to the next case, when an object is placed beyond the center of curvature of the concave mirror. In order to frame the image, we will consider a ray starting from the object and incident parallel to the principal axis. As seen in the figure, after reflection, it will pass through the focus of the lens. Another ray passing through the center of curvature of the lens will simply retrace its own path. Both reflected rays will meet between focus and center of curvature of the mirror, forming a real, inverted and diminished image. Now moving to our next case, wherein the object is placed at C. Here we will consider two rays starting from the object. The first one, which is parallel to the principal axis, will pass through the focus after reflection from the mirror. Another ray, which passes through the focus of the mirror after reflection, will become parallel to the principal axis. Both these rays will meet at the center of curvature, forming a real, inverted and same sized image. Moving to our next case, when the object is placed between the center of curvature and focus of the mirror, again we will take two rays starting from the object. The first ray, which is parallel to the principal axis, after reflection from the mirror will pass through the focus of the lens. Another ray, which is passing through the center of curvature, will simply retrace its path after reflection from the mirror. Both the rays after reflection will meet beyond the center of curvature of the concave mirror, forming a real, inverted and enlarged image. We have tried to frame this image on our apparatus. Let us just have a look at the image formed. Now we will consider the object to be placed at the focus of the concave mirror. We will consider the first ray starting from the object to be parallel to the principal axis. After reflection, it will pass through the focus of the mirror. The other ray could be chosen to be the ray which is passing through the center of curvature of the mirror. This ray will simply retrace its path. The image this time will be formed by a beam of parallel rays. But we know that the beam of parallel rays do not meet. Then where is the image formed? The image will be formed at infinity. Such an image will be a real, inverted and highly enlarged image. Moving towards our next case, when the object is placed between the focus and the pole of the mirror. Here, we will consider a ray starting from the object incident obliquely on the concave mirror, making an angle I with the principal axis. This ray will get reflected, making an equal angle r with the principal axis. Another ray could be considered to be the ray which is passing through the center of curvature. The surprising fact will be the thing that these two rays would be required to be produced along the opposite side in order to form an image. Such kind of an intersection of the reflected rays will be due to an apparent intersection, but not an actual intersection. Therefore, the image which will be formed will be a virtual and erect image. As you can see in the figure, the image is virtual, erect and enlarged. You can see the position, nature and size of the image in the table shown in the slide. Now, we will discuss the images formed by convex mirrors. We can notice that since the focus and the center of curvature lie behind the mirror, there can be only two cases. First, when the object is at infinity, and second, when the object is not at infinity. As you could see in the figure, the object at infinity is represented by a beam of parallel rays appearing to converge at focus, forming a virtual, erect and diminished image. Now let us consider the case when the object is not at infinity. The object can be placed anywhere in front of the convex mirror. The ray which is parallel to the principal axis starting from the object will appear to pass through the focus of the mirror. Another ray which is directed towards the center of curvature of the convex mirror will simply retrace its path. These two reflected rays will apparently intersect at a point behind the convex mirror, framing a virtual, erect and diminished image. The position, nature and the size of the image can be seen through a slide. Now let us move over uses of spherical mirrors. Concave mirrors are commonly used in torches, searchlights and vehicle headlights to get a powerful parallel beam of light. They are often used as shaving mirrors to see a larger image of the face. The dentists use concave mirrors to see large images of the teeth of patients. Large concave mirrors are used to concentrate sunlight in order to produce heat in solar furnaces. Convex mirrors are commonly used as rear view mirrors in vehicles. They always give an erect, though diminished image. Also, they have a wider field of view as they are curved outwards. Convex mirrors are commonly used as rear view mirrors in vehicles. They always give an erect and diminished image. Also, they have a wider field of view as they are curved outwards. So students, we have arrived at the end of today's lesson. Let us recapitulate what you have learnt. You have learnt differentiate between convex and concave surfaces, erect and inverted images, as well as real and virtual images. You will be able to draw ray diagrams showing the convergence or divergence of spherical mirrors and also make ray diagrams pertaining to the image formation by spherical mirrors. You have also learned to measure the physical quantities such as focal length of a concave mirror using appropriate apparatus. You are now able to give uses of spherical mirrors in day-to-day life. So let us experimentally frame the image formed by a concave mirror when the object is placed beyond the center of curvature of the mirror. Here we have taken a concave mirror having a focal length of 25 centimeter. The object is placed at a distance of 63 centimeter from the mirror. Let us see where the image is formed. As you could see, a real inverted and diminished image is formed at a distance of 42.5 centimeters, which happens to be between the focus and the center of curvature. So therefore, we can conclude that when the object is placed beyond the center of curvature of the mirror, the image is formed between the focus and the center of curvature. The image formed is real, inverted and diminished. Now, let us experimentally frame the image formed by a concave mirror when the object is placed between the focus and the center of curvature of the mirror. Here, as you could see, we have placed the object at a distance of 35 centimeters from the mirror. Clearly, the object is lying between the focus and the center of curvature of a 25 centimeter focal length mirror. The image is clearly formed beyond the center of curvature. The image is real, inverted and enlarged. So students, with this we end today's session. Keep learning, keep practicing. Thank you.